Here's a wild idea for you. The AI you use every single day, it doesn't actually think. Not really. It just calculates, and it does it instantly. When you ask it a question, there's no pause, no moment of internal deliberation. It's just predicting the next word based on a massive web of patterns. But what if that could change?
What if we could build an AI that actually processes information step by step? One that can reason through a problem, maybe even change its mind and become more and more certain of an answer the longer it thinks about it. Well, this isn't science fiction anymore. It's the core idea behind a brand new architecture from Sakana AI called Continuous Thought Machines, or CTMs for short. And this slide right here, it gets to the heart of the problem. Current AI is what we call feed forward. You put data in one end, it does a bunch of math in the middle, and an answer pops out the other. There's no real sense of time. But our brains, they're completely different. They're dynamic. Neurons fire in these complex waves, and the timing of those waves is everything. The folks at Sakana AI argue that this instant, timeless calculation is a massive limitation, and it's a big reason why AI still struggles with things like common sense. And that is exactly where this new approach, the continuous thought machine, comes into play. It's designed to bridge that exact gap, to build a system that doesn't just calculate an answer, but actually follows a process to get there.
Now, here's why this is such a huge deal and why you should really be paying attention. One of the co-authors on this paper is Linus Jones. If that name sounds familiar, it should. He's one of the original creators of the transformer architecture. The foundation that powers pretty much every major AI model today. So when a pioneer of the current paradigm starts exploring a radically new path, well, something really important is happening.
So how in the world do they do it? Let's break down the 3 core breakthroughs that make these CTMs so different and, well, allow them to mimic a thought process. Okay, first up, we have something called thought ticks. Imagine you're solving a tough puzzle. You don't just glance at it and instantly know the solution, right? Of course not. You look, you think, you reconsider, you try an angle. CTMs do something very similar. They have their own internal clock, which lets them process the same piece of information, like a single, static image, over and over again, taking multiple thinking steps to arrive at a conclusion. The model's literally creating its own time to think. Second, and this is just wild, each neuron acts like its own little mini brain. See, in a normal AI, a neuron is a pretty simple calculator. It takes a number in, does some math, and spits a number out. But in a CTM, every single neuron has its own tiny neural network attached to it. It actually remembers its own recent activity and uses that history to decide what to do next. This creates this incredibly rich, dynamic behavior, where some neurons oscillate and others spike at just the right moments. And third, and this one is a real game changer, is something called neural synchronization. CTMs don't just care about what each individual neuron is saying. Instead, they look at how groups of neurons fire together over time. The model is basically asking which neurons are working in concert right now. That pattern of synchronization, that rhythm, that becomes the information the model actually uses to make decisions.
So the theory is pretty mind-bending, I'll give you that. But what does it actually look like in practice? Let's dive in and see how all these ideas actually translate into some pretty amazing capabilities.
To test this out, the researchers gave the CTM a really difficult maze-solving task. And the results? Well, they were genuinely eerie. I think this quote from the paper says it all. The model wasn't just spitting out a solution, it was exploring the maze in a way that looked just uncannily human.
And this slide really shows you how tough this challenge was. The CTM couldn't just draw a line on the maze. Nope, it had to output a sequence of moves, left, right, up, down. But here's the real kicker. They gave it zero positional information. It had to build its own internal map of the maze from scratch. And the most incredible part? Nobody programmed this pathfinding strategy into it. It emerged, completely on its own, from the architecture.
But here's the real proof in the pudding. They trained the CTM on relatively small mazes. Then, they threw these giant, complex mazes at it that it had never seen before. Traditional models, they completely failed, just fell apart. But the CTM, it performed dramatically better. And the reason why is so important. It hadn't just memorized the solutions to the small mazes, it had learned a general strategy for how to solve mazes. And this incredible ability to develop strategies on its own isn't just limited to something like mazes. The CTM also applies this whole thinking process to another classic AI task, classifying images.
And this right here is just fascinating. For easy, obvious images, the CTM figures out the answer in just a few of those thought ticks. It's quick.
But for harder, more ambiguous images, it naturally takes more time to think. As this chart shows, the longer it thinks, the more certain it becomes of its answer. And this whole idea of adaptive computation, thinking harder about harder problems, again, nobody programmed that in. It just emerged all on its own.
Okay, so let's zoom out for a second. What does all of this actually mean for the future of AI? Why is this potentially such a massive deal?
When you put it all together, what do you get? Well, CTMs are introducing some truly groundbreaking ideas. First, you have adaptive computation, where the AI itself can decide how much thought a problem actually needs. Then you get superior generalization, because it's learning strategies, the how, not just memorizing patterns. It's a huge step closer to the dynamic, time-based way our own brains work. This isn't just another incremental improvement. It's a potential shift from an AI that just calculates to one that actually reasons.
Which of course leaves us with a pretty profound question. We've just seen an AI that can take its time, that explores possibilities, and that adapts its own thinking process to the problem at hand. It's a system that doesn't just give you a final answer, but seems to have a genuine thought process. So, could this be it? Could this be the dawn of a new kind of AI? One that doesn't just compute, but truly begins to reason?